Pressure of the atmosphere decreases as you go higher up. So if I take this balloon and I think about the pressure forces that act on it, there's a difference in the pressure that acts on the bottom of the balloon and the pressure that acts on the top of the balloon. And so the difference in the pressure forces creates a net force on the balloon. And what's the direction of that net force? We'll give you some choices. Well, if I have a higher pressure on the bottom, lower pressure on the top, I'm going to get a net upward force on the balloon, and that's a real force. It's called the buoyant force. And this balloon experiences a buoyant force. Now, it turns out that the weight of the balloon is bigger than the buoyant force, and so it still falls. But if I were to take this balloon and fill it with helium, the weight would be less than the buoyant force, and so in fact, it would float. Now, as this balloon fills up, notice this. It's displacing a certain amount of air. There's a certain amount of air that is not where the balloon is because the balloon is and the helium that fills it. And so it's displacing a certain amount of air. Okay? So I've displaced a certain amount of air. I filled up this balloon just the same as the other balloon, except here's the difference. It's filled with a lower density gas. And so there's a buoyant force on it. There's a higher pressure on the bottom than there is on the top. There's a net upward force, and the net upward force is bigger than the weight, and so that balloon will rise, okay? But the buoyant force is real whether it rises or not. And we calculate the buoyant force by looking at the displacement of a fluid. So if I take something and immerse it in a fluid, and air is a fluid, so we can have balloons immersed in air, or water is a fluid. I can immerse something in water. Watch the displacement. Here's a bowling ball. And if I take a bowling ball and immerse it in water, you can see the displacement. The water level rises. The bowling ball is displacing the fluid. And I can feel right now, I don't have to work as hard to hold this ball up because there's a weight force pulling down, but there's a buoyant force which is pushing up. There's a buoyant force which is pushing up. Now this bowling ball will actually sink. But if the density was lower than the density of water, the buoyant force, when it was completely submerged, would be bigger than the weight force. And why this is, we derive in chapter 13. But you know this. If I have something which is less dense than water, it'll float. And this is a lightweight bowling ball. This is only 8 pounds. Now it's the same volume as this 16-pound ball, but its mass is half as much. And so as a consequence, its density is half as much. And this bowling ball, even though it's heavy, will float. And it floats because its density is less than the density of the fluid in which it's immersed. Now, you'll see various problems in the chapter that have to do with calculations of the buoyant force. And the buoyant force is a real force that acts on any object which is immersed in a fluid, be it air, be it water, or some other fluid. Now, question for you. I've got a rock here. And this rock has a density that's a few times the density of water. And so if I take this rock and I put it in water, you know that it will sink. But it's possible to immerse this rock in something in which it will float. What would have to be true about the fluid that I put this rock in order that it would float? We'll give you some choices. Well, this refers back to what we talked about earlier. If I want the rock to float, I have to immerse it in a fluid that's more dense than the rock. And the only fluid I know of that meets that criterion is mercury. And I have a bowl of mercury here. It's about 13 times as dense as water. And so if I take this rock and I set it in the mercury, what happens is it floats. And this rock will float in mercury. And it's a real rock. The reason it floats is because the fluid that's immersed in is extremely dense. So the bowling ball floats because it's less dense than water. The rock floats because it's less dense than mercury. So both of these, we would say, are buoyant. But the buoyant force applies whether an object floats or whether it sinks. Right now, because I'm standing where I am, there's 68 liters that is not where I am because I'm taking up that space. I'm displacing air. So as a consequence, there's a buoyant force on me. And so when I stand on a bathroom scale to measure my weight, the weight that I measure on the scale is not my true weight. Here's a question. Is the weight that I measure on the scale higher or lower than my true weight? We'll give you some choices. Well, let's look at the forces that act. If I'm standing on a scale, there's an upward force on me from the scale. That's the reading of the scale. There's a downward force on me due to my weight, but there's an additional upward force, that's the buoyant force. And since I have two forces pointing up and one force pointing down, you can see that the force of the scale on me, which pushes up, that's the scale reading, is actually less than my weight. So when you stand on a scale, the reading is actually slightly less than your true weight because of the buoyant force on you. Now, it's only about 1/7 of a pound or so, so it's not a big contribution, but it's real. And for very, very precision measurements, it's noticeable and it's measurable and it's something that you have to take into account. Now, one other thing I want to point out, if I take this rock and I immerse it in the mercury and I let it go, it bobs up and down. This is an example of oscillatory motion, and it's that oscillatory motion which is the next type of motion that we want to look at in the next chapter.